Chapter 9 is all about normal subgroups and factor groups. So we're going to start with what is a normal subgroup, and once we know what normal subgroups are, we're going to be able to talk about factor groups and then some applications for factor groups. So a subgroup H of a group G is called a normal subgroup of G if AH equals HA for all A in G. We denote this by H normal subgroup G. So this little triangle here is read as normal subgroup. Our first theorem gives us an official test to see if something is a normal subgroup. You can use the definition of a normal subgroup, or you can use the normal subgroup test when you're trying to think about and talk about normal subgroups. So the theorem says a subgroup H of G is normal in G if and only if X inverse is a subset of H for all X in G. As we look at our first two examples, we're really going to rely a little bit more on our definition than the theorem. Example 1, it's actually solved for us already. It just gives us examples of normal subgroups. It says every subgroup of an abelian group is normal. And if you think about what an abelian group is, you know that an abelian group is a commutative group. So this is because AH equals HA for any A in the group, and H is always in the subgroup. So now think about the center of a group. Is the center of a group always a normal subgroup? We know the center of a group is always a subgroup, but is it normal? And to answer that question, you might have to go back and look up your definition for the center of a group. So if you need to, press pause real quick, go back, look up the center of a group definition, and then come back as we start to explore this solution. So yes, the center of a group is always normal. And this is true because of our definition of a center of a group. AH equals HA for any A in G and any H that's in the center of our group. So now factor groups. Let G be a group and let H be a normal subgroup of G. Then the set G slash H, and we're going to read this notation instead of saying slash there. What we're going to read this notation as is the set, the factor group of G by H. This set is equal to AH such that A is in G. Now this notation here should make you think cosets, right? Because that's what we've been talking about before our long break. So we are going to be looking at cosets here as we are looking at factor groups, and we're going to be looking at the cosets as a group of cosets. So this set of cosets where we have the factor group of G by H is a group under the operation AH times BH equals ABH. Now, if we are under addition instead of multiplication, then we'd be saying A plus H plus B plus H would be equal to A plus B plus H. So it works with multiplication or with addition. In our first example here, we're actually going to be using some addition because we are going to be talking about addition because our group here, our group G, is under addition mod 18. So we're letting G equal the set of integers mod 18 under addition. And then our subset, our subgroup specifically, is going to be H equaling the cyclic subgroup generated by 6. And it says find the factor group of G by H. We're going to be taking pieces from G, elements of G, and adding them to H, and listing out all of our different unique cosets, and then we just want to list the simplest ones, the ones with the smallest coefficients. So our factor group of G by H is equal to 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, and 5 plus H. And we can see an example of an operation here. Since this is under addition, we would be combining this 2 and 7 under addition for 9. But as we can see, 9 plus H is not part of our group. But we can simplify this 9, right? We can simplify it by modding 6 because H is absorbing multiples of 6. So we're able to absorb it to 3 plus H. From there, we're going to move into some theorems, and the rest of the chapter is going to be fairly theorem heavy. And so I'm just going to kind of read through the theorems with you. So theorem 9.3, let G be a group and let ZG be the center of G. If the factor group of G by the center of G is cyclic, that means G is abelian. So this gives us a way of determining if G is abelian if we know something about the center of our group and the factor group of G by its center. Theorem 9.4, for any group G, the factor group of G by its center is isomorphic to the inner automorphism of G, that group of inner automorphisms. Theorem 9.5, let G be a finite abelian group and let P be a prime that divides the order of G. Then G has an element of order P. Now this gets us ready for internal direct products. So we talked about external direct products, now we're talking about internal direct products. So an internal direct product of H and K. We say that G is the internal direct product of H and K, and write G equals H times K, where we're actually going to use an X for multiplication here. If H and K are normal subgroups of G, and G is equal to H times K, and the intersection of those two normal subgroups is equal to the empty set. Now it's going to help for us to look at an example here. So we're going to look at D6, and we are going to let F be just some reflection, and let RK denote a rotation of K degrees. So D we could then say is equal to R0, R120, R240, F, just some reflection, R120, F, and R240, F. And this is taken with the internal direct product of the set R0 and R180. Now I do encourage you to read through your book and play with some of the examples that it gives you in your book as we're thinking about internal direct products. Hopefully by the time we get through the end of the chapter here together, you have a good working idea, but your book has a lot more examples that can clarify what an internal direct product is and how to work with it. Now, we can take internal direct products of more than just two subgroups or groups together. So let's let H1 through Hn be a finite collection of normal subgroups of G. We can say that H is the internal direct product of this collection of normal subgroups and write out that G is equal to their internal direct products. And this is true as long as these two bullet points hold. Really, this is just an extension of our original definition of an internal direct product when we were just looking at H and K, two normal subgroups. Now we're looking at a larger collection of normal subgroups. So, Theorem 9.6, if a subgroup of G is the internal direct product of a finite number of subgroups, H1, H2 through Hn, then G is isomorphic to the external direct product of H1, H2, all the way up to Hn. So here we're seeing some sort of connection between internal direct products and external direct products, which is kind of nice for us as we start thinking about what we know and understand, because we know a decent amount about our external direct products. So just real quick for review, when we're using an X, we're saying internal direct product. When we are using this plus sign with a circle around it, we are saying external direct product. So we have internal and we have external. Now at this point, we're able to classify groups of order p squared. So every group of order p squared, where p is a prime, is isomorphic either to z sub p squared or zp external direct product zp. So this notation didn't show up very well here, so let's me rewrite that for you. That's zp squared. That is what that notation is saying. Sometimes my LaTeX typing doesn't look too pretty. And then we're left with one last corollary to wrap up the chapter. If G is a group of order p squared where p is prime, then G is abelian. So that wraps up chapter 9. I'll be doing another video for you guys going through a few examples that we would have normally done in class. Of course, email me as you have questions, reference your book, read through the extra examples that your book has, and hopefully between your book's examples and then the next video that I do working through some example problems, you'll have a good hang of chapter 9. If not, shoot me an email and I'm more than happy to talk through some things with you.